then in 1915, Einstein proposed general theory of relativity, and he had different predictions for it. And so often if someone comes up with something new, effectively the reaction is something like, this is crazy. And that was at that time as well with general relativity. People are very keen to not overthrow what they have established, and it takes a lot. And one thing is required often is to have a unique prediction about a phenomena that you can go and observe and see whether it's actually valid or not. And one of these unique predictions is the gravitational lensing effect and its strength particularly. And so this is the Eddington experiment in 1919. This is basically the next solar eclipse that occurred somewhere where people can go and put on telescopes, and they could measure the stars first when there was the sun not there at night where the location is, and then right at the position when the solar eclipse happened. And there is a slight deviation of the position of the parent positions of the star. And this was really the breakthrough effectively, where people start accepting the reading what actually Einstein proposed, etc., that becomes established. So this was really the key experiment on the road that now we have so many confirmation of the theory in many scales. Just want to highlight that part was really one of the cornerstones and the anchor of what general relativity is and how it got experimentally confirmed. And just keep that in the background. And then now where we are now, maybe strong lensing can play such a role again in different domains of fundamental physics or astrophysics, depending on what we want to probe. What is lensing, or when is it strong? The way we define it is effectively when we see a certain object multiple times on the sky. So strong lensing here doesn't mean that the bending is incredibly strong. It's defined by, even if the bending angle is very small, that we see objects multiple times, or they're highly distorted, even on very small scales. So this is not strong gravity. This is a different, even everything here is very weak in the bending angle. So that sketch here could be drawn at 1915, and it was drawn in the 20s of, there is theoretically the possibility to have actually the same objects being seen multiple times on the sky. But it was mostly a nice, we call it Gedanken experiment, a thought experiment, a toy, but was never really explored whether it's real or not, and definitely not by Einstein. And then skipping a few decades, in 1979, so pretty recently, relative to 1915, there was an object found, and this is a quasar, or a twin quasar, which had the same properties, so exactly the same spectra. They were separated by about 6 arc seconds. And in fact, with follow-up efforts, it was shown that this is actually the same identical object, so that and thus needs to be strongly lensed. When we have more recent observation, we can even see, this is with the Hubble Space Telescope, we see the 2 quasars and actually a galaxy in between that acts as this lens to cause this effect. So it took a long time from the theory to the actual observations in the late 1970s to do so. Lensing itself, the optical effect, is something we are very familiar with since centuries, effectively. And here I'll show you a movie of some fish, and you see, or may see it on the screen. I don't know how well the Zoom connection works. You see effectively that the fishes appear multiple times, and the reason for this lensing effect is the different diffraction index of water and air, and so that the light effectively travels a different path, takes a curve. This is the classical optical regime of lensing that's been seen here. Another optical regime is when you have glass. So here it's a wine glass. It's courtesy to Phil Marshall, where when you put these in front of here a candle, you see the candle being shed on here in effectively an Einstein ring. And it's interesting that the optical properties of the bottom of a wine glass are very similar to the optical properties that gravity induces in bending light. So in that sense, all the language that we are going to use in this course is an optical language. In describing the phenomenon, we just have to identify the source of this effect to either a diffraction index of material like glass, or to a diffractive indices of matter that bends space-time in that regard. And what really has revolutionized this strong lensing as a cosmological and astrophysical probe is with the onset of high resolution imaging, and in particular Hubble Space Telescope. Here just a gallery of lenses from the SLACS Sloan Lens ACS survey. These have been spectroscopically found and then followed up with Hubble, and these amazing pictures occurred. So this is an effect that is often on very small scale, very faint. And so with these large ground-based telescopes or space-based telescopes, this phenomena became imminent. And here just an illustration of how light travels through the universe and reaches us around a galaxy in between, leading to this distorted multiple imaged arcs. Another regime here is a beautiful image that you may have seen often, and I keep staring on it, are galaxy clusters. So this is the largest gravitationally bound structure in the universe, and background sources can be, these clusters effectively a very efficient lens, massive, leads to large deflection angle, and sources in the background, galaxies get highly distorted, and you see these highly distortions all over the place. And you can even see secondary distortions around individual substructure, so to speak, of these clusters. And this can be really used to probe the mass distribution of the universe, to shed light on what is dark matter, where is it structurally speaking, and how much is it from basically the size of the Einstein ring of this phenomena. What has also been discovered is basically time travel, or almost. This is here an image of one of the galaxy clusters, where it happens to be that there's a spiral galaxy in the background that got lensed. So here, this is one image of the spiral galaxy. Here's another image, and then this is the same galaxy as well, appearing again. And that happened to have, in one of the images of the Hubble Space Telescope, you see this blob here, where effectively a supernova went off, one of them, and here it's already quadruply imaged. And from that, one could predict the time delay when it's going to arrive and appear in this image here. And the reason for that is twofold. So one is there's different geometric paths that the light is traveling through, as well as different location in the potential where the light travels. And so this results in a relative time delay. And so even if we see the supernova exploding, or when it reaches us, it happened like billions of years ago, we can get a prediction of when we see it over there. So it's almost time travel. Obviously it's not, but this time delay effectively allows us to anticipate what we're going to see in a delayed image. So This was discovered in 2014, and an expected delay in the next years, or now it's in the past, so a paper should come out very soon, describing the delays and also measuring the Hubble constant. I come to that. And unfortunately, these other images here we missed. Here, this is more than 50 years. This is about 20 years or so. It was in the past, so if we had a telescope, we could have actually seen this. But here, a missed opportunity. And so there was a prediction here that this should appear in the future from this one. And well, scientists were right. And at one point when they kept monitoring, they actually saw the blob appearing where they expected it to appear. And this just marks our incredible understanding of what gravitational lensing is, how we can compute and make predictions that we can validate, and not just a posteriori, but actually make a prediction and we get it effectively right in the position as well as when it occurs. So déjà vu already seen in that sense. The next few slides, I go a bit through some science questions. I know this is not all of them, and happy to discuss and go in detail to some more in the future, but just to give a bit an idea of what questions we are nowadays tackling with this rich phenomenology. So one is dark matter. So we know, and don't go into details of all the experimental or observational evidence for the presence of something that we cannot explain by the baryonic matter. So we need an additional matter content in the universe that shapes the appearance and the dynamics of the universe. And the different hypotheses, and one of the most prominent ones, are cold dark matter, which is mathematically speaking just a cold fluid that we solve. We don't really know what it is. It can be a particle that just has enough mass to act as a cold fluid. Or another one is warm dark matter. It could be like a sterile neutrino that is lighter and thus damped structure in the early process of its production. It could free stream, and so damped structure at small scale. And so if we could image the universe and these are predictions effectively of how the universe would look like on galactic and subgalactic scales. If we could image these matter distribution, we can immediately tell is one or the other or both excluded or a very viable candidate of dark matter. The problem is we can't directly. So what we see is normally the smallest structure are dwarf galaxy or ultra-faint galaxies that we can see mostly just around our Milky Way, and if they're a bit more luminous further out to a few megaparsec. And that's all we can see. And both theories, or at least to some degree, remain valuable under these two hypotheses, because both theories can predict some number of small-scale structure that may or may not host dwarf galaxies. The ultimate questions that we have is, are there completely dark structure that are depleted of baryons and in particular stars? And thus we cannot use stars or any other baryonic tracers to shed light or to probe these theories. And here comes strong lensing into play. It's uniquely placed to really only solely trace gravity. It doesn't care what type of matter it is. It doesn't care whether it hosts stars and its light or any exotic material. The only thing it really cares is it matter that spans space-time. And so this is a unique probe to explore this regime, this untested regime of CDM or potential discovery space for alternative models of dark matter. And so this technique, here an example here from the literature, this is from Vecchetti et al. 2012, where they have from here a keck, this is a Mauna Kea at an 8-meter class telescope with adaptive optics through modeling, and we come to this in the second lecture then, made indirectly a detection of such a clump. Doesn't really know whether it's completely dark, whether it has a few thousand stars, but this is a solely gravitational detection of such structure. The same or similar can be done, for example, with ALMA, interferometric data. It's even higher resolution in certain wavelength. This is work by Save 2016 that did basically reconstruct the presence of such a clump near one of the arcs here marked with the cross. Another technique, also using gravitational lensing, is by making use of flux ratios. So it's known as the flux ratio anomaly. What it means is you measure the fluxes of these quasars, and you have a prediction what is the ratio between the flux and one image in the other. And the question is, how much is it perturbed relative to this prediction? And perturbations, for example, can be caused by small halos of dark matter. And here's an image. This is a model here done by Daniel Gilman, the former PhD student I worked with, where he basically simulates such an image, effectively a quasar accretion disk or a narrow line regions, to be a bit more precise. And what the movie here shows, it drags a clump of dark matter through it. And what you see it's being slightly distorted. And what you see on the left is the overall perturbation of its flux that we measure. And so we have several, about 10% flux distortion being caused by such a structure. Is there any question so far? Just please interrupt. I just want to give some space. All right, for now, we go into detail in this example then on Thursday. Another example of an application I want to measure that you may have heard of and someone introduced has already worked on is measuring the Hubble constant with time delay cosmography. So I mentioned the possibility to measure a time delay or to predict a time delay between multiple images due to the different light path and where they travel through the potential. And another additional component we require to predict the relative images is the absolute scales in the universe. So how far away is actually the lens source system? So is it closer or is it further away? And depending on that, you predict a shorter or longer overall relative time delay. And so you can turn that problem around and effectively measure this distance ratio here while when you predict the geometrical quantities. And so if you measure then a time delay, if you measure this guy here, you can measure absolute distances, and absolute distances you can turn in, okay, a certain absolute distance at a certain redshift means there needs to have been a certain acceleration between us and then, and this is the Hubble constant. And so the Hubble constant is effectively a distance measurement turned into a statement of how fast the universe expands with the redshifts included. This is known as time delay cosmography. Here, back this image you have seen. Here, I'll show you some time series where it's a quasar is being monitored, and the flickering of the quasar images are correlated, and the correlation of it is the time delay. And so you may see when certain things start rising in the different images, and then you can measure such a time delay. Here, another example of a time series that goes over multiple season, winter and summer, and you can probably by eye guess a time delay between the blended images A and B, where things rise and fall, and also image C. And so this gives us the ability to use this time delay method to actually measure distances. Another thing that's here in the light curve, such as a transition, is microlensing of stars and potentially black holes that perturb very small sources. This can be quasar accretion disks or even individual stars there are behind. And so this can lead to quite high magnification pattern. What you see here is such a magnification web. If you're interested, we can also go dig a bit into this type of phenomena. It can be used to measure the size of accretion disks and effectively learn about how quasars, black holes effectively accrete their material, how they grow over time. And another thing that I haven't mentioned here, you can actually detect planets with it due to this distinct microlensing feature in our Milky Way and in Andromeda. So the last aspect that I want to show, just to give you a very broad overview of where strong lensing in one or the other way comes in, is you may have seen this image, I think about 2 years ago, was everywhere in the press, and it was advertised as being the basically the first ever image of a black hole, which is a correct statement. It's just also, when I looked at it as a wait a moment, I've seen this, and this is a strong lens. So what you see here is actually strongly distorted paths where the light here, this is radio effectively, went around. So the intrinsic structure looks completely different. It's actually, we think it's more like a jet going out, and what we see here is the back of the jet being warped around, but it's really ongoing research of actually de-lensing, so to speak, this image to see what's actually in the intrinsic structure of it. So I can also change the title a bit here with Photoshop. Astronomer captures smallest results of strong lens with this observation, just to link to different science where this can be required knowledge to be used in strong lensing phenomenology. And last but not least, here is a gallery of lenses that collaborators of mine have recently in the last few years discovered. What you see here is multiple imaged quasars. And on the left here, where you have the telephone numbers, so we give these objects names due to the coordinates and what kind of survey has discovered it. On the left, this is the real data from Hubble Space Image in multicolor image. And on the right is a model of it that was generated by a software due to, well, with the modeling and requirement to actually match the data. And so we have, for all these lenses, we have models where we think what the phenomenology of strong lensing is, as well as the light distribution of both the lensing galaxy as well the background being captured to a certain degree. So we will dig also a bit into how we actually make these models and to what we can use them. And so goals, I've mentioned it, or are there any questions until now? Please feel free to interrupt. I may not see the chat, I just need to monitor it. Yeah.
I have a question.
Yes, please, go ahead.
You said that you can use the lensing to measure the redshift of different objects. So maybe with the lensing, we could like get a hint on the Hubble tension. Is this possible?
What was the last thing on the whole?
On the Hubble tension.
Yes, and we do that actively. So we are not, okay, so to clarify, we're not measuring the redshifts with strong lensing. The redshift is the easiest part we can get from a spectrograph. By basically putting a spectrograph on it and see how much the lines are being shifted relative to what they intrinsically are. But once we have a redshift and the time delay, and at the same time, we have an understanding of these distortions, we can actually, yes, measure the Hubble constant through this distance. And that's what's known as time delay cosmography, and that's in active use. Correct.
Okay, and these measurements are in agreement with one of the two ways of measuring the Hubble constant, or is like a another problem, let's say, because it won't fit the other two data or the other two
Uh,
predictions?
That's a great question. It's basically an entire talk to see whether or not they are consistent. Short answer from me is they are currently consistent with both answers, but we were very actively work on to allow for the precision that only one answer is allowed. And this
Okay.
is completely independent of any other systematics that may or may not be present, be it in the CFIT, distance ladder, or the CMB, or any other anchor. So it is a completely different physical anchor of the scales of the universe. And so in that sense, we need independent confirmation of a certain tension or, overthrown our model. And so the more independent measurements we have that reach the precision required, that each of them individually can actually tell at least, well, there is a problem. Alexander writes in the chat, the measurement of HL from holy cow are, yes, the holy cow measurements are in 3 sigma tangent, but they assume certain density profiles. And if you relax these assumptions, which I've done last year, then you actually are consistent with the CMB. And this is then the TD Cosmo papers that came out last year. TD Cosmo 4 is the paper reference that I'm talking about. And so it is an ongoing debate on what assumptions are justified, and the stakes are high. And to overthrow certain paradigms, it's important that we crucially investigate all the assumptions that we have made and whether they're actually justified to the level to claim a discovery. And that's the current process also within the CFIT community. It's ongoing, and there's been put scrutinies on measurements and really an active ongoing debate. And every year so far, I basically give a bit of a different talk on this topic. In that sense, it's very exciting, but I'm not here saying it's either one or the other.
Okay. Thank you very much.
Any other questions or comments? No, then I just quickly, I've mentioned the goals here, just I listed them. I can give you some basic understanding of strong gravitational lensing, gaining intuition in the phenomenology and potential science applications, and also gain hands-on experience with software in analyzing data and experimenting with the phenomenology. And that last part will be incorporated in the first ones as well. So this is probably the only one where I give this one way slides. So the structure of the course, most of the session will be interactive Jupyter notebooks. This will be on Google Colab or locally with your Python environment. So you get both possibilities. Interlude slides. So this is basically an interlude or a starting slides as we had here. Group or individual exercises and explorations then while working on the notebooks. And we can adapt to what you are interested in and what you want to learn. So many of these notebooks provide sort of like starting examples in many directions, and you can decide on in which way you want to go and how deep you want to go into certain aspects. And as I also mentioned, there's more resources will be linked and more notebooks are available, be it from basic examples to effectively end-to-end analysis on real data. And so this more structured lectures is more like a start off that you be more able to go and gain actually hands-on science experience as the starting where you actually know where you can dig further in. And that's basically the end of my slides. I stopped sharing the slides. Any last questions here. Other than that, I'll link here in the chat. As you may have already seen, you're in the strong lensing a lecture in on Slack, and here also linked the GitHub. And what you see there as well is a link to a Colab notebook. And here's the link as well. So first, what is Colab? Does anyone have worked with Colab Jupyter notebooks? Raise your hands. Nice, I see already many hands. For those who didn't raise, don't worry. So when you click on this link, what happens, what should happen is, I'm gonna share my screen again. Please click on that link and open the notebook on your browser. And yes. And what you should see is such a Colab logo, SL Basics, IPython notebook. And what this is a virtual environment somewhere in the cloud that allows you to execute basically a Jupyter notebook, which is an interactive terminal, so to speak. So you can execute command Python in that case, as if on the command line, and go box by box. You can have the play, you can have the possibility to run a certain set of section, and that allows you effectively to define a workflow of your interface with a software, with data, play around, and have this interactive experience. You can do that locally, so the link to the GitHub repo is here, also provided here at this GitHub repository, and here you find also the lecture effectively here. This is the same notebook as I just shown in Colab, here just in GitHub, which you cannot execute. This is just displays the same thing, and you can either fork, clone, or download it and install it locally as well. So you have different possibility to work with them. Colab is very nice because it doesn't require you to set things up previously. And so the first exercise for you is basically click this button and see. Now what you see here is the requirement is already satisfied, but what it will do is first it installs Lenstronomy from the PyPI server, as if you do a pip install numpy, etc. And there's a specific requirement on this PyChaml that needs to be fulfilled that should overwrite whatever PyChaml has in the running notebook. And corner as well is a plotting routine that for some things we require. And so this is a block where you can execute, and there's other blocks that are plain text or markdown, and so adds nice in the documentation. You can edit these all by yourself, and you don't have to worry to overwrite what I had on mine. You can also save it to your space and further play around. So you have all this possibility to play around with it in that regard. I linked here some lecture notes that go in more details. Some of the things when you click on it, you see very familiar aspects that are in the notebook. So where I took the resources from as well, just as a start. So click on installation, and for a test, you can also click on one of the first rows here to see whether there is no error occurring and whether these calculations actually run. Are there any questions or problems occurring while opening and start running the notebook? so far not. It doesn't mean that it's for everything working, but I just currently just assume it, but please step in if you're not. So in this second part of the lecture, we go in some nitty-gritty mathematical details, but also directly link them on actually doing the calculation. So all the math we will execute in code with the software Lenstronomy, which you also here automatically installs it through PyPI, but the entire source is publicly available. It's an open source software that you can get here from my GitHub repo, Lenstronomy, that has a documentation as well. So, and you can also go and see actually where certain calculations are being made. You can go through it either through the read the docs link here. You find all the documentations of the source code of certain lens model module. That's mainly what we're going to use. Where is it? In this part is the lens model package with these type of operations. So going back to the notebook, so I had provided here some lecture notes for additional material. And so we start here, and this is really the key part of how we do lensing, how we write the equations down, the formulation based on it. So I want to spend some time of it. So if you understand this part by the end of the lectures and the family, then it's already a mission accomplished to some degree. So this is the lens equation that we call. So what you see here is 3 different planes. We call them the observer, the lens plane, and the source plane. This is a simplified expression of how we describe lensing in the regime where there's one strong or dominant deflector in the universe that does most of the bending. In that case, the lens plane is the plane responsible for the bending. The bending of light occurs right here between the straight line and the deflected one going here. And this deflection, this physical deflection here caused by this plane is alpha hat. That's how it's being described here. When we look at an object, we define a certain center straight line, effectively a coordinate system where 0, 0 is. And this theta angle is where on the sky we see a certain object. And so we see an object on the sky at angle theta, means we think it's over here, while in reality it's bent here by alpha hat, going this way, and where it actually is, it's at a position eta away here. And the relation between theta and eta, so to speak, is how much physical deflection being caused and how long it has been going from here to here and from here to here. And that is basically this first equation here. It's the distance here described in the theta coordinates here, which is a physical scale in the lens plane, which is the distance times the angle here. And so this first equation describes that mapping between, depending on what these distances are, when I see something at angle theta, it's being deflected by alpha hat, where it's on eta. This is this first deflection. In terms of angular coordinates, and that's mainly what we see on the, well, that's what we see in the sky. So we would like to stay with angular coordinates as much as possible, because that's what we see on the sky. So the angular coordinates here, this is effectively a definition of the angular, of these distances, which are called angular diameter distances, which basically means that the angular diameter distance time a certain angle gives you, by definition, the physical scale in that plane. And so beta here is the angular scale where the actual source is. So this beta times ds is this distance here. So beta is the position in the source plane if there were no lensing. So if I remove the lens plane, the light ray would have passed in this dotted straight line. So this is beta. Now we can describe what we call lens equation, which is the difference between where we see something on the sky, theta, minus where it actually supposed to be on the sky without lensing, beta. And the difference between these two angles we call alpha, without a hat. So beta is theta minus alpha. This is, in that sense, a very straightforward statement of a definition of so alpha effectively is the distortion or the displacement vector effectively between theta and beta on the sky, describing the lensing. This alpha, however, is not directly alpha hat, because alpha hat is a physical deflection at a specific plane, and so depending on where this plane is, we need different alpha hats to get the same mapping between theta and beta. So, and the relation between alpha hat and alpha are the ratio between the distances ds, this guy, and ds here. So if this guy here is 1, so if the ratio of ds and dds is the same, basically meaning that this guy here is occurring right at the same position, then the angles are the same, the moving is the same. So if the shift happened right at the observer, we need to shift physically the angle the same way we actually look. And the further away it is, actually the distance ratio here, this guy is smaller than 1, and so we see actually things being moved weaker on the sky than it's actually physically being bent. So this is the lens equation. Beta is theta minus alpha, and this is the schematics that leads to this. Any questions so far? Silence. Okay, so you can also, if you don't understand it, it's a nice homework problem just to rederive these equations from the schematics. It's yeah.
I have a question. In this part of, or in this equation, where we have the thin or the thick of the lens plane, or we're supposing it's just a plane and very thin.
Here we suppose that all the deflection happened effectively at one plane, which is obviously never really the case. Matter always has some three-dimensional properties. The idea is effectively whatever you have in terms of a galaxy or a galaxy cluster is relative to the size of the universe, very small. So that is the assumption we're making here. And okay, the generalized formulas, and I come to that, is you can set a lot of multiple layers. You can slice the universe in ever smaller pieces and then redo the calculation. And what then happens is that the rays follow a certain zigzag course, depends on, at each layer they get deflected. And the limit of slicing it to infinite layers is then the actual proper true path of how smoothly light rays travel through the universe. The approximation here is mostly valued because the deflection angles are so low. So this is an extremely accelerated deflection. Normally they're of order an arc second, which is much smaller than, I don't know, this is like 10 degrees or so. And so lights only slightly deviate from a straight line, such that this deviation is only a higher order perturbation to the calculation.
Okay, thank you. Good.
Yeah. And so, yeah, so here comes the deflection angle calculation. So here we start from GR, and I just saw I have a typo here, it's a factor of 4 is missing. We start from GR with a physical deflection angle caused by some mass M, which is a point source, or we can think of it as a point source at an impact parametric psi. We can then integrate a lot of point masses in terms of like a density and integrate over the density. And we arrive that the physical deflection is this quantity, while this integral here is along the Z, so along the projected axis, along the path of the deflector, while this is the angular, or the physical, in angular direction, effectively the coordinates. And this is then the mathematical form of having the impact parameter, basically a form of the coordinates with its absolute values. So this can then be simplified, and we can write this inner integral as effectively a mass density of a sheet. So this is the density of the universe, or of the deflector, integrated along a specific path at the specific angular or position that we see it. And so we can think of this capital sigma as a mass density of such a sheet. So how much surface mass density there is. This is this sigma. And now we can write with, from box above, that is the same definition alpha and alpha hat as we had right here. We can now write this alpha, which describes the mapping between where we see things to where it actually comes from, as this guy. And we can write that alpha is this integral or in units of angles on the sky of this quantity, while this guy here is, this is just a definition basically of the surface mass density divided by this critical surface mass density, which sums up all the prefactors of the angular diameter distances, G, the gravitational constants, and C. And so this guy we can write down as an integral of the convergence. I'll come to that in the next block, what is another meaning of it. And so that's how we can compute these lensing quantities. If you give me or someone else some mass density, that's the way we can compute these deflection angles to first order in the weak regime of gravitational force. So here in this next part, you can execute this line. Should be a quick execution. What we do here is we set up, we do these calculations for one simple lens model. We set up a class instance of lens, and you can, even when you put the cursor on it, you see actually what are arguments of this class or function, which is pretty nice. And so we import here from Lenstronomy such a lens model module. And we say, like, we want to have a lens model that consists of one singular isothermal sphere. This is basically a mass density that falls off with a power of 2 and results in a homogeneous velocity dispersion of everything that's orbiting within. Leads also to constant rotation curves, effectively, if it's a rotating body. So we set the parameters of this model here as with an Einstein radius of 1 arcsecond. And here we set the centers to be at 0, 0 for convenience. And now we say like theta, so on the sky, we have here 2 coordinates at 1 and 0.02. I just randomly put them in and asked now, what is the deflection angle of this guy? And here are the 2 components of the deflection angle alpha, which is a vector, goes in both directions. I can also compute and ask what is ray shooting here, what is when I shoot effectively the ray back, where in the source plane it lands, and this is beta x and beta y. So that's where the rays actually came from originally. And now the last thing, I just test whether the lens equation holds, whether theta minus alpha equals beta. And that's basically under the hook the calculation that's been done. So this is trivially satisfied from the software underneath, but conceptually, that's what the lens equation means. So we have beta coordinates, we have the deflection angles, and we have theta coordinates. And here it's just one simple exercise that computes that. Yeah, that's basically it. And you can, yeah, there's a hand raised, yes.
Yes, I'm wondering, like we're starting here the almost equal. It means that we're allowing for an epsilon difference. Like how do you set that? Or, I mean, how do you actually calculate the almost equal thing?
So there is always some, or can be potentially some numerical difference of how the calculation's being done. So computers have finite precision always. And so there can be some bit floating. And so 10 decimal places is something that I here define myself as a requirement. That means for me, it's equal if it's 0 point and it's 0, 0, 0, 10 zeros effectively, or 9 zeros and a 1. That's what I currently demand them to be. If I can also print both statements, this calculation, as well as beta x, and execute them. And here you see that effectively they are the same to all the floating points. Here I didn't know how precise Colab is. So the Google Cloud in doing this, you can define the precision at 15, and it hopefully also passes. If you go to higher precision, I'm actually not sure, because at one point the computing machine, okay, it's identical floating, but it may be that the computing machine uses a bit of different operations, and then certain rounding errors may occur. So that's why I was quote unquote conservative in my test and just said 10 decimal digits are fine enough.
Thank you.
Yeah, my pleasure. Any other question so far? So yeah, this is very technical, but I just want to go through it. So the next concept is the lensing potential. So in a single lens plane regime, so we can introduce a scalar lensing potential, here psi, such that the deflection angle, which are here called the reduced deflection angle, so the ones that we see on the sky, and not the physical one, is the gradient of the potential. So the derivative of the scalar in one direction is the deflection angle in that direction. And the derivative of the scalar in the other direction is the deflection angle in the other direction. And in that form, we can write the lensing convergence as half the nabla square, so of that operator. So the gradient of effectively of alpha as well. And we can, using the identity here of like the differential of the logarithm, resulting in this guy, which this guy here is effectively this here. We can write the potential, or we can calculate the potential as being the convergence being integrated as a logarithm scaled from where on the plane effectively it is. So you can, as an exercise, you can try to differentiate these equations, and you will end up that one differentiate leads to alpha as defined here. And the second differentiate is if you integrate, you actually get the convergence here. And that also highlights effectively when we talk about convergence, it's meant in a vector field way. And it so happened that the lensing convergent corresponds in this regime to effectively a scaled value of the mass density on the sheet. So one is a geometrical quantity convergence, the other is a physical, the sheet of mass, or the surface mass density, and they happen to be related through this critical density definition. So it's very neat to get this analogy of a physical intuition of what it is and the mathematical form of it, which is nice, but is not something that is often mixed in the literature. I just want to highlight conceptually how and where these come from. And as done for the other quantities, here we can also evaluate the potential here, and you get a value for that at any position, and you can put it in other positions for theta, and you get a different value. So a bit further down, you will be able to play around. So one of the last concepts of today is the Fermat potential and time delays. And so what we can define here is another scalar function, which we call Fermat potential, here written as tau, which is a combination of a geometrical term, so the square of the theta minus beta, of effectively the path difference between a straight line and your deflected path, and the lensing potential that's been introduced above. And the extrema of these functions mean where this function results in the gradients of it, where this function has a plateau, either be a maxima, a minima, or a saddle point. This is this expression. In this extrema, by design of this function, it satisfies the lens equation. Being extrema of this function happen to be such that the actual source beta maps to where we see it theta. So it satisfies the lens equation, and that's where images appear. That's one way we can actually solve for where images appear. And there is a theoretical concept you may have heard of, Fermat's principle, or Huygens principle. And these are optical principles that state that light rays travel in extrema of the arrival time surface. And so this Fermat potential effectively happen to be, surprise, being the time delay, so how long it takes, or how much longer the light ray takes relative to a straight path without lensing, where we can actually interpret this first point as the geometric quantity, and that last time as the Shapiro delay, so the lensing potential, where in optical language, this is effectively a diffraction index, meaning that light in this medium travels at different speed, and that then causes also the bending angles. But you may say, like, wait a second, but in GR, in general relativity, there's no such things that light travels at a different speed. It's always the speed of light, and it's at the core of this theory. That's true if you are in a local reference frame where this light passes. But in a potential well, be it a galaxy cluster or on Earth, clocks are ticking slower. And so if you observe it from further away, on a different clock, you actually see the light being traveled faster or slower. So, and from that external observer, the one that receives the light at the end, the experience is different, and so this term is effectively that Shapiro delay. So this here is then again, here we can execute the Fermat potential, these quantities for the same parts. And now the last one is time delay. So this Fermat potential here is in geometrical units, meaning this is arc second square or radian squared, just some angle squared. It's not in units of seconds or day. And what is really missing here is the overall path the light travels through. And to turn these angulars into physical quantities, these distance ratio here is required. What is also required is this gives a distance. And if we want to have a time and we know the speed of light is c, we divide by c. The 1 plus set d, while set d is the redshift of the deflector, is because we see also the effect of the lensing being redshifted. That also stretches the time delay that it experiences when we measure it at a later epoch of the universe. So this is the stretching of the overall effect itself. And for convenience, here, this is just a definition. We can define such a time delay distance, which is just the overall sum of all these geometric terms together, because we cannot distinguish when we have a handle on the Fermat potential and measure time delay. We cannot really distinguish what type we are actually measuring. And the overall thing we can constrain or is relevant for the time delay prediction is what we call here the time delay distance. This comes out of this. And we can now make such a prediction for a time delay, and this is done here in the next block. For the time delay prediction, we need a cosmology, or we at least need to know these distances. And the way we do it here, we set in, we making use of AstroPy in its cosmology module, and set up a specific cosmology, set up also the redshifts of a lens and source, and here we plugged in some number, and then computed the arrival time at this position. And you get here a number out. And if I were to change the Hubble constant, quick questions. If I change the Hubble constant from 70 to 140, how much will the time delays change? Will we measure a longer time delay, or will we measure a shorter time delay? Those who say longer, thumbs up, and those who say a shorter, thumbs down. And a small hint, you can all run exactly the same calculation in your notebook. Did someone manage to run the example? Silence, or am I still connected?
Yes, you are.
Oh, yeah. So if someone wants to share the results, or I can click here. And I can click here with 140 of the Hubble constant. And what happens it's 11 days, while at 70 we had, or almost 12 days, here we had more like 23 days or 24 days. So the larger the Hubble constant, the shorter the time delays. So what this means, a large Hubble constant means that you need to expand faster to a certain redshift, which effectively means that the distances involved in the universe are shorter. And so it's a shorter Hubble constant is actually longer distances and a longer age of the universe in the expansion, while a larger number is actually a shorter scales in the universe. And this is then reflected. And so if we have excellent measurement of some time delay, we know everything, and we want to know the difference between is the Hubble constant 74, which here gives a prediction of 22.6 days, or 67, for example, which gives here a prediction of 25 days. So there's a 3 days time delay difference between a question that you really, really want to have an answer to. So that's one of these parts. Any questions? And yeah, feel free to also change, for example, the redshifts of the lens and source. What this does, it changes these distances. And so you will get a different answer for the time delay. So suddenly see, I moved the redshift and the time delays change. I see a hands up. Please go ahead.
Yeah, I think it's me. I'm wondering about how are the different angular distances are measured in practice. Also, is there a correction to the source's redshift due to the lens, the lensing, or something like that, or just assume that the effect is small?
And we assume the effect is small. So the redshifts are measured with spectral line. So how the shift is. In this redshift range of 0.3 and higher, peculiar velocity, so how actually physically objects are floating around in the universe, are very low compared to the cosmological redshift. So these errors are relatively small overall in that regard, if this is the questions you had.
Yeah, thanks.
Yeah. And another question, please go ahead.
Yeah, I'm just wondering, like trying to figure out the result you just showed, that the longer the Hubble constant is, the shorter the time delay will be. And I'm wondering if it's because, well, we have a product here of the ds, and then over the ds. So basically all of these angular distances are like go with the inverse of the Hubble constant, and then basically we're going to have a final angular distance, and that's going to go with the inverse of the Hubble constant. Is that right, or it's not necessarily why that's
absolutely correct? Yes. So that's the Hubble constant is, as you said, inverse to the distance to a certain redshift. And what we are actually measuring is something with units megaparsec, or something with unit absolute distance. And it's a mix, it's convolved between 3 different redshifts, so it's not to one single redshift, but all these redshifts equivalently scale with the Hubble constant. So it's the normalization is the same for all those. And so indeed that factors out.
Okay, thank you.
Yeah, excellent point. Yeah, any other questions so far? If not, okay, I thought it was the last one, but no, there's another box before we come to illustrations. And this is distortions and magnification. So this is really fast, I know that, so can go back in the notebook, and we can even redo certain parts tomorrow as well. So distortions and magnifications. So we have the lens equations, theta minus alpha equals beta, and we can differentiate them. So we can take the differential. How does, in that case, the source move if we change the image position slightly? So we can differentiate the equation. And this is known as the lensing Jacobian, which is here A, which here is the definition of it. It's differential of the lens equations. So it's differential changes relative to how the image and the source plane changes the angle. And this is effectively differential size changes in different directions. And this second part is using the lens equation again. So this is the Kronecker delta, and here the deflection of the alpha divided by theta. And we can also then write this guy as here the second derivative of the potential. So, and we can write that down as a matrix locally for a specific direction with convergence, and what we have introduced here, shear gamma 1 and gamma 2. And here are basically the definitions of what convergence is in this language and what the shear terms gamma 1 and gamma 2 are, which are basically just read from this equation here, how they're formulated. And they satisfy specific geometrical properties that we come to in the next section. And this distortion matrix is particularly useful as it locally quantifies how something gets distorted, depending on how it looks in the source and how it looks distorted. Not just how it looks distorted, but what it effectively does, it changes the area element. So if something is like round, and then after the lensing ellipticity, it may also have changed its size. And the change in the area element is what we call the relative or the lensing magnification. So if something becomes larger, it also becomes brighter in total flux, as we see it on the sky. And so the lensing magnification, or the magnification in general, is how much flux we measure that is being lensed, divided by how much flux would we have received if there were no lensing. And this is the determinant of a distortion matrix is the area or the volume element, or in 2D, the area element. And in that case, the way we defined the differential from the source plane to the image plane, what we have here is from the image plane to the source plane, it's the inverse of it. And so the magnification is effectively in this matrix language, or you can compute the determinant, this times this minus this times this, and what you get is this quantity here as well. So this is the magnification. Highlight is that lensing does not change the surface brightness of an object. The magnification is solely due to area changes. So if you see a star being magnified by lensing, it is basically, if you zoom in, the surface area of the star is actually changing. And it's not that the star itself, if you look at the surface of the lens star, changed its brightness or its colors or whatever. So it's a totally distortion effect. We just call it magnification when we cannot resolve it. So just to point that out, this is the lensing magnification. And here we can compute these quantities in the second derivatives, the same, we choose the same theta and the same lens model. We can compute the Hessian, and the Hessian is effectively all these elements of this guy here, the second derivatives. We can compute the kappa quantity, we can compute the gamma quantity, gamma 1 and gamma 2, and we can compute the magnification. And what I here test is basically whether this formula here and here holds for these quantities. So is the magnification really 1 over this quantity, which is the same as this guy here? And are kappa, gamma 1 and gamma 2 defined such that they actually adhere these quantities here, just as a test. And you can run that as well. So now, a lot of theoretical quantities, and you may not know, so why have I introduced this? What is it good for? So the next thing is here a bit a longer example of where we illustrate these quantities. So what we make use here are some plotting routines that just simplify some of the plotting and the amount of code we spend in this line. And what we do here is a bit more complicated lens model. We choose a singular isotherm ellipsoid. So we make the mass distribution in projection a bit elliptical. And we introduce an additional lensing term that distorts, shears the observables. And here we put in the parameters. Here the Einstein radius. Here two eccentricity components. I'll come to that later. This is the way to one way to define ellipticity. You can also define it as an axis ratio and an angle. And in this way here, it has some advantages as come later. And the center. And two shear quantities in the two direction. What I also define here, I want to have a source at a certain position that I want to see where they actually end up being imaged. So that's the first block. I define my lens model. Feel free to play around with this. In the next part, I define a grid where I want to evaluate these quantities that we have discussed, the Fermat potential, the Hessians, magnifications, etc. These are some plotting quantities configuration. And so here I do the plotting. So here first, I plot the lens model. And what you see here is for this specific model here, this is the answer. Well, you barely may see it here, a star. This is the same as this guy. This is where the actual image is in terms of beta. And that lensing effect made this image appear in A, B, C, and D, where A, B, C, and D are ranked in terms of arrival time. That's just a convention that's being used here. What you also see here in black or gray, this is the convergence, so the mass density of that profile. You may see it, guess a bit slightly elliptical. In red, this is the line of, you see it also here in the magnification mu. This is the line of effectively infinite magnification. This is where a point source becomes infinitely magnified, which is a bit strange because nothing becomes infinite in a real universe. And it's actually true because nothing is a point source. Everything is extended. And so everything that is finite is still having a finite distortion because this is really only a thin line, mathematically a line that is infinite. This is it's what we call the critical curve. We can shoot these red dots back in the source plane, and what we get is the green lines, what are called the caustics. And so if you're within the inner caustics, you get 4 images. If you're outside, you get 2 images. This is a geometrical quantity that defines of when you get certain multiplicities. So this is the first part. Then the second one here, this is the Fermat potential. You see here lines of equi-Fermat potential for the given source position. And you see that D and C are saddle points. The gradient of the Fermat potential is 0, but they're saddle points, while A and B are either maxima or minima in this position. And there's another, to say there's a 5th image that's not been shown here, and that is straight through the center. So at that maxima, or at that minima, so to speak, that is infinitely demagnified. So it basically has no volume, but it formally exists. You also, we can, for example, here, just as a plot the shear, gamma 1 and gamma 2 values of this profile and the deflection angles. And you can try around moving the source around and redo and see how the lensing effect change. And you see that the image position slightly changes. You can even go a bit more extreme here. What's happening if we move it further out? And yeah, you see the configuration suddenly changes even more. And if you even move further out, we only get 2 visible images. Yeah, you see here, it's just 2 images, and that's how then the Fermat potential and the image positions look like. While these quantities here are only the deflector field, which in that case we haven't changed, but I can do so by just increasing, for example, the ellipticity. Let's go a bit extreme and put some significant shear in here as well. And you may see that lensing properties significantly change here, how the caustics look like, how the magnification curves look like, and you see even these parts being distorted here. And that's, yeah, and you see the convergence here is rather elliptical now, as I boosted it. I'll give you 5 minutes, play around, and I stop sharing here. And if some of you played around with some values and can show like how your favorite or whatever what you plugged in resulted in, that would be nice to share with us. So go ahead and play around with the lens model parameters, and don't worry, you cannot crash anything. It's just a Colab notebook. And in the meantime, if there's some questions, please let me know.
Sorry, Simon, maybe you said it and I missed it, but what other models are available to play with apart from the isothermal sphere?
Good question. So there are many models to play around with. So I'll just share my screen again. When I go to Lenstronomy, you find here a list. This is in the lens model module. You find here a list of profiles, and these are all the different profiles you can use. And there are, I think, something like 30 or so. I don't really count them. And what you can also do is when you go to the Colab, here I use a superposition of 2 profiles, so an SIE and a shear. And I can also add another singular isothermal sphere, a third one. And this is then, I can basically add the parameters of this third profile. I give it another Einstein radius, which I make rather small. I give it a certain center position, which I happen to give somewhere close to critical curve. And I'll make just the shear a bit smaller and click enter. And what I get is this model here. And you see here this extra lensing effect that I happen to plug near that critical curve is distorting this critical curve here. Yeah, so there's many lens models to play around. And the one we just played around was the SIE model, which is this guy here with the eccentricities, and the SIS model. I think that may not have been so well documented, but here you see effectively what the convergence looks like. And then the functions we called are the derivatives. And you can even go here to the source, what's actually being calculated when a deflection angle is calculated, and that's the Python code that's being used under the hook. So, stop sharing. Did anyone successfully or tried plugging in some numbers and either doesn't know what happened or just one or two that share their screens? Oh, I'm not sure you can actually share screens, or maybe you can now. Who wants to go? Through Zoom, it's hard for me to distribute chocolate or so on for people that did contributions. Just one or two examples that people played around just to share.
You can say a random name and see.
Okay, I see a random name. I just scroll down and say Oleg on the spot. You wanna?
Yeah, honestly, sorry about that.
No worries.
Yeah, I was following your presentation, so I didn't mess a lot with the code. So I basically be showing the same thing that you did.
All right. Okay, I call on. I'll just scroll it. Atalia, do you have a notebook that you just share? Don't worry, do. Atalia, are you here?
Yeah, sorry.
No worries. Yeah. You want to share your notebook just to show everyone what you clicked around?
I'm basically the same as Oleg, so sorry, I haven't played with the parameters.
Did anyone have some other parameters plugged in? And all right, I see a hand. Nice, Luis.
Hi, I just changed the position of the source. Yes, and can I share my screen or?
Yes, try, and we have Luis here in case there is some issue.
Okay.
Perfect, nice.
So basically, I just change these two numbers here.
Yes.
And I was comparing with the results in the original notebook. And I just find a change here in the Fermat potential.
Yeah.
Comparing with the original notebook. So I don't know what this means, but I find a change. I found a change.
Yes. So the Fermat potential depends on where the source is. And so effectively here, it shows that, well, the Fermat potential is really a function of the source position. So if you move the source, that Fermat potential that relates to that specific source position is changing. And so the time delay service or the arrival time service for that source position is changing. And so it changes where the images appear as well. And you moved here the source out by 1 arcsecond, so pretty far out. And it's basically what you now see, you have only 2 images that you see. One is, in fact, oh no, you only see 1 image. So there may be, it may even be so much out that you don't see multiple images anymore. Yes. And so that's the normal solution for most of the lensing effects on the universe. You don't see 2 images because they are not so close to such an overdensity. And so what you can play around is actually moving the source slightly inwards and see when multiple images occur. Another possibility that may have happened here is that there is another images, but it's outside your plotting. So you can also increase or decrease the frame, the window, which is the combinations of delta pix and num pix. So the if you scroll a bit up. So, yeah, so util.makeGrid. This is basically defining the coordinate grids of where it computes these quantities and where it plots it. And so for the default of 0.02 arc seconds with 200 pixels per side, it means it's 4 by 4 arc seconds. And you can also either change the width of the pixel in arc seconds or the number of pixels, and you get a larger or smaller window.
Okay. So I can change this.
Yes, and click replay. And see, you see, aha. And now you see two images. So one was just outside of the window where it was plotted. Yeah. And in that case, it's almost one will be very demagnified B, and A will be almost the intrinsic magnification. So it will be not as much strongly magnified. Yeah, very nice.
Thank you.
Yeah, thanks for sharing. Yeah. Anyone else that found something? Yes, I saw a hand. Francisco.
Yes, Simon, thank you very much for your lecture. I have a question. Can you say something about possible degenerations between the time delay distance and the Fermat potential in order to obtain the time delay relative?
Yes, so this is in that sense a detailed questions about lensing degeneracies and how well we can actually learn the Fermat potential from observables. So this will be, I can make an example of this for the next session that you can play around and see. So there is the mass sheet degeneracy, which limits our access to what that Fermat potential actually is from observables. And so in the beginning of next session, so we stop here, but you may already see below, there's a list of points of observables. And then we go into, okay, what actually can we extract? So far in the notebook, we have computed quantities for a given model and say like, how does, if we put X into lensing, how does it would look like? And the next step is we turn it around. What if we have certain information? What can we actually know about the lensing observable, about the underlying lensing properties? Yeah.
Okay. Thank you very much.
Mm-hmm. Any last questions? Yeah, so for that sense, I think this is a good point to stop. I run through a lot of material. I'm totally aware, both the slides I were pretty rapidly through, as well as here the notebook. We go through a lot of probably new concepts for you. So I suggested the homework to digest those, maybe play a bit around with this, specifically the last one, gain a bit of intuition. And then next session, we start from the block we have stopped. And with the observables, we go into a bit intrinsic source sizes. We actually predict surface brightness that is distorted and take it from there, actually how we can use this modeling. So I will prepare the notebook for Thursday, and I suggest the homework is basically play around with that notebook. You can also, if you don't want to have it on Colab, you can download the notebook and locally set up the environment, be it either with your Conda forks or pip install. In particular, lens astronomy here is required probably on top of what you have installed. And if you have questions, let me know. I see another question. Please go ahead, Lutz.
Yeah, it's a quick one. I'm wondering if there's a particular scale that we're working here, because I don't have like intuition for the scales in a typical configuration with two lenses. and I actually plug another source. And I'm getting the images and everything, the shear and the potentials, but I'm not sure in which scale I'm working at right now. So for instance, I have one with 1.5 and 1.3. The other one is like minus 1.3 and minus 1. So I'm not actually sure in which physical scale I'm working right now, or the results that I'm getting right now.
Okay, yeah, okay, that's a good question and may not be so well documented. I'll just quickly share here. So the scales here are angles in arc seconds. So in that sense, this is from here to here is 1 arc second. And so the images here are separated by about 3 arc seconds. And so your center 0, 0, for example, that's what I put in for the deflector is basically here at 0, 0. And the images here appear here and here. And the one that I added here just to show this additional SIS deflector, I put in, let's come up here at 1.4.3, which is 1.4.3 here. So this is the scale here. So in these parts, it's just units of the pixels. So I haven't put in a rescaling of the scale bar of the plotting. So that was only for this part. So scales here are all units of angle on the sky. And the convention here I use is arc second. For these types of lensing calculation, it doesn't really matter whether you use radian, arc seconds, or minutes. All the differentials are basically the same. But as soon as you want to compute physical units, like the time delay, then it matters. And the convention here for the time delay is in arc seconds, such that we can compute what is actually a time delay here. This is of units, tens of days in that configuration. Yeah.
Great, thank you.
All right. Any other last questions or comments? Yeah, let me, if you have questions in the meantime, let me know. Ping me on Slack is probably convenient. And I'll prepare, we will continue this notebook